Hi, class. In this presentation, we're going to focus more on the molecular physiology or the molecular anatomy of a skeletal muscle fiber. In the previous recording, we focused on the groupings of structures within a skeletal muscle cell or skeletal muscle fiber. Now we're going to focus on the myofilaments within the myofibrils, those individual filaments that make up the myofibrils. So to back up a couple slides here, if we look at a standard generic skeletal muscle cell, we have the individual cell, and that individual cell is going to have myofibrils within it. Those individual myofibrils are going to be broken up into myofilaments, here represented by the purple and the pink line. As we look at our myofilaments, there are two variations. We have the thick filament, which down here is going to be the purple filament. Thick filament is made of many myosin molecules. One myosin molecule kind of looks like two sperm wrapped around each other with a crooked head on the end. And if you take many myosins and combine them together, you can get a myosin filament with the heads sticking out from the central shaft. And what do these myofilaments do, or what do these thick filaments do? They help to arrange for contraction of the muscle, to take the chemical signal to contract and turn it into physical motion. Because of these tails on the individual myosin molecules, we're going to have a bare region in the center of all myofilaments with the heads pointing out to the left and to the right. We also have thin filaments. Thin filaments are overwhelmingly going to be made of actin proteins. And when we think of these actin proteins, I want you to think of these individual red balls that are kind of a spherical or globular protein. And we're going to have these G-actin subunits or globular subunits strung together to make a fibrous filament of actin. And attached to the thin filaments, we're going to have some accessory proteins as well. For instance, we have shown in kind of a orangish yellow color here, we have a troponin complex. And this troponin complex is a calcium binding protein. And when calcium attaches to troponin, troponin changes shape. And as troponin changes shape, it's going to pull on, and I'm going to use, let's go with blue here, kind of this bluish strand. This is a tropomyosin molecule. And this tropomyosin will get pulled on and serves to block active sites on the actin G subunits. So when calcium comes into this thin filament, it binds to troponin, troponin changes shape, and then tropomyosin is pulled out of the way so that the active site of the actin, the site of actin, can be exposed. And we'll talk about those in a little bit more detail in just a moment. But first, let's go back up and stay on a gross level. We'll focus on myofilaments. Myofilaments, or the thick and thin filaments, can overlap with each other. To help keep them connected to each other, we have some elastic filaments. And these elastic filaments are shown in this diagram as the light blue springs. And these elastic filaments are going to be anchored to one end of a thick filament and to a structure known as the Z-disc, which zigzags back and forth. So we can think of the elastic filament as a band of elastic fiber that goes from Z-disc through the core of a thick filament to the next Z-disc. Excuse me, to the M line in the center. I misspoke there. Now, the individual proteins that make up the elastic filaments are referred to as titin subunits. Multiple titin subunits combined together make a single elastic filament. This is how we can have the elasticity or some of the recoil of our skeletal muscles. These elastic filaments work in conjunction with the collagen fibers that are present within our muscles. Contractile proteins in our myofilaments are the proteins that physically cause the muscle to get shorter. They are the business end of our muscles, and those are the myosin and the actin. We also have those regulatory proteins, the proteins that control whether or not actin and myosin will contract with each other. or overlap, have increasing levels of overlapping with each other. The regulatory proteins that we've talked about are tropomyosin and troponin. So you can think of the tropomyosin and the troponin as the on-off switch. To turn them on, we need to expose troponin to calcium. The calcium will be released from sarcoplasmic reticulum, go across the sarcoplasm, and then bind to the troponin. Troponin, when exposed to calcium, changes shape, and then tropomyosin is tugged out of the way to expose the active sites of the actin. Now, as we're looking at the myofilaments, we're going to need some way to anchor those myofilaments to the cell membrane of the muscle fiber, or the sarcolemma of the muscle fiber. And one of those key proteins is known as dystrophin. Dystrophin is clinically very significant because there are some diseases associated with mutations to dystrophin. So let's talk about dystrophin that's working normally. Here we have a dystrophin filament shown in red. And this dystrophin filament serves as a way to take a myofibril and link it to the cell membrane, or the sarcolemma of the skeletal muscle fiber, so that when these myofibrils contract, that skeletal muscle fiber as a whole gets shorter. And if we have any genetic defects of dystrophin, we're going to have the disease state muscular dystrophy set in. As we look at these striations, the banding patterns of our skeletal muscle fibers, we'll see, particularly in skeletal muscle fibers, shown here, for example, this is classic skeletal muscle with very big, bold, beautiful striations. There's a dark area, followed by a light area, followed by another dark area. Let me clear the screen here. There we go. So we have alternating dark and light bands. Dark bands are technically referred to as A. A stands for anesiotropic. This is really not anything I'm going to test you on, but in case you're curious, the reason the A band is called the A band is because the A bands take photons of light and reflect them or refract them different ways so that when you look at it straight on, it appears dark. The I bands are where light travels directly through the myofibril. And as we look at those I bands, we can have an I band right here. The I bands are going to change as the muscle relaxes and contracts. When we contract a skeletal muscle fiber, the I bands are going to get shorter. The A bands are going to stay approximately the same, though. Now, in the middle of our I bands, we're going to have a dark line. That dark line right in the center of the I band is referred to as the Z disc. We have Z disc there, another individual Z disc, another individual Z disc, and we have more Z discs over here. It's worth emphasizing the structural and functional unit of a skeletal muscle is the sarcomere. And if we take one Z disc and go all the way across to the next Z disc, we have the sarcomere, which is the contractile unit of a myofibril. As we're looking at the middle of the sarcomere, we're going to have the M line. So think of the M line as the middle point of the sarcomere. We're also going to have an H band. This is a part of the A band. It's not as dark. So in the very center of our A band, there's a region where a little tiny bit of light gets through. Those white lines in the center of the A band refer to or denote H bands, and then the dark line in the center is the M line. Now, when we think of I band, the light band right here, I will stand for isotropic. So light will travel the same direction after going through the I band. So if we have a light bulb on the backside of this cell, the light will go straight through the I band and then hit you in the eyeball. So it appears brightly colored. Light can travel through it, as opposed to the A band, the azeotropic band, where photons of light are scattered in different directions, as opposed to hitting you in the eye. So the A bands are dark, I bands are light. I've already mentioned the Z discs, which are in the center of the I bands. One Z disc to an adjacent C disc denotes sarcomere. And now we focus on the sarcomere in more detail. So we have a Z disc here, Z disc here. This is one big sarcomere. I'm going to say this again. It's the functional contractile unit of a muscle fiber. This is where the action's at. When we contract a skeletal muscle cell, we are going to cause one Z disc to get pulled closer to the adjacent Z discs. In other words, our sarcomeres get shorter. And they get shorter when the thick and thin filaments overlap more. A common misconception is that the thick and thin filaments change length when we contract a sarcomere. That is not correct. Thick and thin filaments will always stay the same length when we contract a skeletal muscle fiber. The thing that changes is the amount of overlap between a thick and thin filament. The more overlap, more contraction. Less overlap, less contraction. As we contract a sarcomere, it causes the myofilament and the myofilament to contract. The myofilaments then pull on dystrophin. Dystrophin is then going to pull on the sarcolemma, and then that sarcolemma will connect to the endomysium, the paramysium, the epimysium, and then ultimately the tendon pull on the bone. That's all we have for this recording. And we've talked about, just to debrief and reiterate, we talked about the structural anatomy of a myofibril, those groups of those bundles within a muscle cell or muscle fiber. So we have muscle fiber. Then muscle fiber is and I'm going to back up several slides here. These terms are way too similar sounding for my reference. Here we have a muscle fiber. A muscle fiber is a bundle of myofibrils, and a myofibril is a bundle of myofilaments. So that's all we have for this recording. If you have any questions, please feel free to shoot me an email or post them on the class discussion board. And as always, happy studies.